I've built this giant racetrack to challenge this rally car. First, it will have to go over this hill, but not too fast, since it could otherwise smash itself into this rotating barrier and get crushed by its metal spikes. Then, it will enter this giant vertical loop that demands the car to go full speed in order to make it through. And finally, after making it through all of the obstacles, it will face this massive ring of fire that it will have to jump through. If the car manages to do it, it will win a prize of $1 million that is locked away inside of the crates behind... No, stop. This is not a Mr. Beast video. There's no $1 million prize, the prize is death, the crates contain explosives. Good luck. Okay, so, very cool racetrack. Spiky thing that will kill you if you cross the speed limit. A loop-de-loop that is absolutely amazing. Very big ring of fire. Ending in a stack of crates filled with dynamite that will blow you to smithereens. Okay, so, are you ready? 3, 2, 1. God damn it, the car has no wheels. Who forgot the wheels? Oh wait, I did. Hello there, my name is Lucas and welcome to Vlog. Today we are going to build a car physics system and put it to the test on this racetrack I created. This is going to be cool. Alright, let's take a closer look at this vehicle. If we zoom in on one of the wheels and remove it, we can see that it is attached to the car by a spring. This spring is the first component we will simulate to build our physics system. To do that, we first need a way to measure the length of the spring. We'll cast the ray down from the spring's attachment point until it hits the ground. We will also need to know what the radius is of the wheels of our car. By then measuring the length of the ray and subtracting it by the wheel radius, we get the length of our spring. I am also going to introduce two new values, our rest length and the spring travel. It's actually really simple. The rest length represents the length of the spring in its neutral state, which is when the spring is neither extended nor compressed. The spring travel then defines how much a spring is allowed to compress or extend. When a spring is compressed, it generates a force that pushes it back towards its neutral state. The strength of this force is called our spring stiffness. What we will do is calculate how much the spring is compressed and multiply that by our stiffness value. The more the spring is compressed, the larger the force will be. Once calculated, we will apply this force at the point where the ray hits the ground and pushing upwards onto the car's physics body. Let's test it out, shall we? The springs do a good job of holding up the vehicle, but it's a bit wobbly. So unless you're trying to win a lowrider contest, or you're some kind of cartoon character ignoring the laws of physics, I'd bet you're gonna have a hard time actually driving this thing. An alternative solution would be to fully commit and turn it into a pogo stick instead, and hopping your way to work from now on every morning. Don't worry, nobody's gonna think you're strange at all. Okay, so how do we fix this wobbly mess of a car? We can do this by adding some damping to the spring. Damping applies a force that resists the spring's movement. This removes energy from the system, allowing the car to settle instead of bouncing endlessly. In order to add this, we need to keep track of the spring velocity. Using that, we can calculate a damping force by multiplying the velocity by our damping stiffness. And finally, we combine the damping force with our spring force. Now, the car finally starts behaving like an actual car instead of a drunken pogo stick. To stress test the suspension, I can throw it into the air a bit and let it land. As you can see, it settles quite nicely. Perfect. We can now move on to steering. At first glance, steering the car sounds quite simple. We have a car, 4 wheels, and we simply just rotate the 2 front wheels. Problem solved, right? Well, let's see about that. I want to start steering the car at an angle of 20 degrees, so I'll give both of the front wheels an angle of 20 degrees. If we rotate just one wheel, everything looks fine. The wheel follows a circular path and behaves exactly as expected. The problem becomes obvious when we also start looking at the left wheel. The wheels turn smoothly, but they start to aim towards each other, and even their paths cross. And if you now also picture that these wheels are attached to each other by a car frame, you can likely also imagine that there's no version in reality where the frame survives the turn like that. We can however fix this by simulating Ackermann steering. Instead of giving both wheels the same angle, we calculate a slightly different angle for each one using the following function. Imagine the car turning around a single point somewhere beside it. That point lies along a line extending from the rear axle. The length of this line is equal to our car's turn radius. We shall use 20 again for this example. Because each front wheel sits at a different distance from that turning point, they need to have a slightly different angle in order to stay perpendicular to the path I just drew. To calculate those angles, we use 2 different measurements. The wheelbase, which is the distance between the front wheels and the rear wheels, and the track width, which is the distance between the left and right wheels. These values represent the sides of a triangle we can draw between the front wheel, its rear wheel, and the turn origin. Using the triangle, we can calculate the angle of each wheel by getting the reverse tangent of the left side divided by the bottom. In this case, the left wheel ends up at about 17 degrees, while the right wheel turns further to roughly 23 degrees. Once we apply these angles to both the left and the right wheel, the car can finally turn the way it's supposed to, without tearing itself apart. Now that we've got our car wheels turning smoothly, let's implement acceleration and get it ready for the road. We know that our car consists of multiple wheels, each attached to the chassis by a spring. These springs can be compressed, causing them to exert an upward force onto the vehicle. In reality, the amount of force a wheel can apply on a vehicle depends on how much load its spring is carrying. In order to simulate this behavior, we reuse the same spring force and apply it in the forward direction too. I've created a scene that visualizes some of the forces acting on the vehicle. The blue line represents acceleration, orange shows velocity, and the green arrows represent the steering direction of the front wheels. As you can see, we are able to move our car forwards and backwards just fine. Problems start to occur, however, once we try to steer our vehicle. While the car does turn to the left as expected, it also begins to slide sideways. Also, steering without accelerating and using only its current velocity seems to have no effect on the vehicle at all. The reason for this is that we are currently not accounting for wheel traction, practically allowing the vehicle to move in any direction, regardless of how the wheels are oriented. We can solve this by calculating the local velocity at each wheel's contact point, and applying the horizontal force in the opposing direction. What this basically does is counteract any sliding that is happening on the wheel's horizontal axis, effectively creating traction. This forces the car to move in the same direction that the wheels are facing. As you can now see, the car responds much more quickly to steering, and when we stop steering, it no longer glides around like we are driving with summer tires during a snowstorm. We can now also steer properly while the car is moving without needing to apply any additional acceleration force, as it properly adjusts to the orientation of the wheels. Driving in reverse works just as well and behaves very similar to a real car. At this point, we have everything we need to make a fully functional vehicle in our game. I think it's time to finally put this to the test. Let's have a driver take place in the driver's seat and make him race. 3, 2, 1, go! The driver launches off the line, but as the hill approaches, he brakes just in time. He floors it again to build up enough speed for the upcoming loop. Finally, he reaches the most dangerous obstacle yet, the ring of fire. He makes the jump and lands straight into the explosive crate, and being blown up instantly. Well, that went over quickly, but I hope you liked it as much as I enjoyed making it. Oh, and for legal reasons, the driver is only temporarily suspended from life. No drivers were harmed in the making of this video. The individual depicted was only temporarily suspended from life due to genetic overachievement. Any assumption, the actual mortality is pretty coincidental and should not be taken seriously. The individual is merely experiencing a brief unscheduled pause in living. That'll be all for now. I hope you enjoyed watching this video, and if you did, please don't forget to like this video, comment, and consider subscribing. Before we move on though, I've created a scene where the driver drives headfirst into this pile of explosions. Enjoy!